Hey class, welcome to bonding. We're going to review the three types of bonds and go a little bit more in depth into Lewis structures, taking it a little bit to the next level. And this is important for the next part of the unit where we get into shapes. So what are we talking about with bonds? We're talking about ionic, covalent, and metallic. So just let's briefly define those. Ionic bonds are the electrostatic attraction between oppositely charged ions. In covalent, we're sharing electrons. In metallic, there's this sea of electrons. The cations of the metals kind of hold all of the electrons in place. I know I've used the analogy before of imagine you've got three of those kind of chest-high tables, and there's food on each of those. There's brownies and chips and salsa and maybe pop on the other one, and it's a party. Those tables are the nuclei, you, the people, are the electrons, and you just freely flow from the brownies to the chips and salsa to the pop. That's kind of what's happening in a metal. Well, why do these form to begin with? It has to do with the electron structure of atoms. Would atoms rather give up and steal electrons? Would they rather create the sea of electrons? Or would they rather just share electrons? And each of these bonds has distinct chemical and physical properties, which will shape everything that we do from here on out. Let's take a deeper dive into the ionic bonding. Remember, with ionic bonding, we're talking about metals bonding with nonmetals. Consider where you find them on the periodic table. If you have something over here and something way over here, can't even get it in the camera, you got ionic bonding. Metals, nonmetals. When you form an ionic bond, it is exothermic, energy is released. Both the ionization energy and the electron affinity can give us some sort of a clue as to whether or not an electron wants to gain an electron or give an electron. And this is a bond between a metal that has a low ionization energy. What does that mean? Metals love to give away their electrons. And it usually bonds with a nonmetal with a high electron affinity, a nonmetal that wants an electron. So if you take a look at the example here, sodium loves to get rid of that electron, low ionization energy. Chlorine loves to take the electron, and they happily do so. And then you get sodium chloride. As I mentioned, the different bond types come with different properties. For ionic substances, we're looking at brittle compounds with high melting points. The reason why they have high melting points is because of their crystalline structure. All the atoms are in a very, very specific patterned arrangement, and we'll get more into that next semester. If you take a look at that picture there, you can see that arrangement. So the crystals can be cleaved, they can be broken apart, but there's so much electrostatic attraction and forces between the atoms that it's very difficult to break them up. Thus, high melting points for ionic substances. Well, why do ionic bonds, when they form, why are those exothermic? Well, when you remove an electron, that's endothermic. That takes energy to remove the electron. Adding an electron is exothermic. Well, we know sodium and chlorine, for example, are very attracted to each other as ions. One's positive, one's negative, opposites attract. This attraction draws them together, and when they come together, energy is released. And the ions form this beautiful solid array or lattice structure, very, very structured solid. And we're going to look more detail when we do a Pogel into lattice energy. But lattice energy is the energy required to completely separate 1 mole of a solid ionic substance into gaseous ions. That does require quite a bit of energy. So what makes lattice energy so large for ionic substances? Well, because there's so much structure and the electrostatic charge between the atoms is so great, it takes a lot of energy to break them up. What affects that? The stronger those ions are attracted to each other, the harder it is to break them up. This is why they have high melting points. What is lattice energy dependent upon? 3 things. The charge of the ions. The greater the charge, the more they stick together. So for example, just sodium and chlorine, they both have charge of 1, +1 or -1. What if you have aluminum with oxygen? Well, you've got a +3 and a -2. The bigger the charges, the more they stick together. The size of the ions makes a difference. Smaller ions are going to bond together more strongly because they can get closer together. Maybe it's not the most appropriate example, but I like to use the example of imagine you want to measure the distance between two atoms. So let's use people. Imagine you have two tall, thin, beautiful, gorgeous models. They're very, very thin, very fit. And put a dot in the middle between their stomach and their back, right in the middle. They each have a dot. These models hug. A real hug, not a fake hug. Real hug. What is the distance between those two dots? Probably not a whole lot. They're small people. They can hug very tightly. Now take two sumo wrestlers. Put a dot between their stomach and their back. Have them hug. What's that distance? Much, much greater distance. Smaller atoms will bond more tightly to each other than bigger atoms. The arrangement in the solid, how those atoms are arranged, makes a difference. And we will get more into solid structure in the next semester, but just know that for now. Lattice energy increases as the charges increase and the radii decrease. There's your overall. The stronger the charges, the smaller the atoms, the more lattice energy, the more energy it's going to take to break up this ionic substance. So let's go ahead and apply what we just learned. Who has the higher lattice energy? Sodium fluoride or cesium iodide? Well, the one thing you should notice is that cesium, sodium, they're both plus ones. F and I are both negative ones. So we don't have a difference in charge, do we? What about the distance between them? Well, we know, based on what we learned in the last unit, that the atomic radius is much, much smaller in period 1s and 2s than down in 5 and 6. Sodium and fluorine are much closer together. So their lattice energy is going to be great. Those are like those two little skinny models clinging to each other. Cesium and iodine would be like the sumo wrestlers. Remember, the trends in lattice energy mimic those for atomic radius, but inverse. As you get bigger radius, the lattice energy is going to go down. It's going to be easier to pull them apart. That's my dog pacing, in case you hear that. Sodium is +1, fluorine's a -1. Why is that? Well, to take away a second electron from sodium would require a tremendous amount of energy. It's not going to happen. Sodium only has one valence electron. And the same could be said for fluorine or chlorine, right? They only need one more electron to have a full outer energy level. And they're not going to take on more than one, because then that means having to move that electron to a higher or energy level, and there's just not enough energy for that. If you really want to get into more about orbitals and energy levels and stuff, you ought to take an upper level chemistry course. It's actually kind of interesting, but we're not going to get into it right now. I love trying to record at home when now the second dog has decided he needs to be wandering around. I apologize if you hear that and it's annoying. All right, let's switch gears. Let's talk about covalent bonds. So in ionic bonds, we were giving away and stealing electrons. Now we are going to share electrons. Oh, they're so friendly. When you look at the Lewis structures for these, and we'll draw a bunch of them, the only difference we're going to change is I want you to use a line that shows an electron pair being shared between atoms. And then the dots represent electrons that are not paired to anything else. We call those lone pairs or non-bonding pairs. And that distinction becomes really important when we start getting into shape. Well, why is that trigonal pyramidal, or why is it whatever? There are different kinds of covalent bonds. There are single bonds. That's one shared pair of electrons. A double bond, there are two shared pairs. And then, of course, triple bond, 3 pairs. And the general rule is that as you go from single to double to triple, the length gets smaller, the number of electrons increases, and it becomes much stronger. So a triple bond is the shortest and the strongest of the 3. As we just pointed out, as you go from single, double to triple bond, they become stronger and smaller. So the stability of a molecule really has to do with how strong those bonds are. The stronger the bonds, the more stable a molecule. And what we call that bond energy is called bond enthalpy. What is the H value required to break a bond? And when you break a bond, it requires energy, so bond enthalpy is positive. But when bonds form, energy is released. And we'll look at this in some more detail later on with one of our pogles. But just know that the greater the bond enthalpy, the greater the bond strength, the more energy it's going to take to break it up. There are 3 different ways to calculate delta H, and you've already seen 2 of them. One was where we rearranged the equations. Remember, we might have flipped an equation to make everything add up to the overall equation. Sometimes you had to multiply through to change the coefficients or divide to change the coefficients. That's one way to calculate bond enthalpy. Another way you've already seen is the weird member sigma. You add up all of the products enthalpy. Don't forget the coefficients. You subtract the sum of all the products, delta H. There's one more way to get it. And we're going to look at that right here. Again, breaking bonds is endothermic. It requires energy. Forming is exothermic. We release energy. So the one way we've already talked about is delta H of actually knowing the delta H values. Well, what if we have the bond enthalpies? So this is a little different here. When we do this one, if you look at the 5th bullet, we're going to do the sum of the bond enthalpies for everything that is broken, and we're going to subtract the bond enthalpies for everything that is formed. So this one's a little different than what you've done before, because where are the bonds broken? The reactants. Where are they formed? The products. So you're going to look at the bond enthalpies for everything on the reactant side, add them up, and subtract everything on the product side. This does mean you have to be able to draw effective Lewis charges. You have to be able to draw Lewis structures. You have to be able to draw them. You have to be able to count all of the, there's 4 CH bonds here. You have to be able to know that, there's a double bond in oxygen. It's a double bond between the 2 O's. All of that is really, really important. And then it's really pretty easy math. So delta H is negative when the bonds in the products are stronger than the reactants. Think mathematically. If you're doing the bonds of the reactants minus the bonds of the products, how are you going to get a negative value? Well, you need to be subtracting a bigger value. So if the bonds in the products are stronger, it's going to be negative. If the bonds in the reactants are stronger, it's going to be positive. It's going to take more energy to break than you're getting when they come together. As the number of bonds between atoms increases, the bond length decreases, the bond enthalpy increases. That makes a difference in your calculations. So when you're doing these calculations, you can think kind of mathematically about it. Look at the bonds, look at the values of those bonds, and who's got more strength in those bonds, the products or the reactants. Let's just quickly summarize ionic and covalent before we move on to Lewis structures a little bit more. Remember, with ionic substances, we're giving away or stealing electrons, and we call these compounds. With covalent, we're sharing electrons, and we call these molecules. Ionic substances are brittle. Covalent, well, they're kind of all over the place. They might be solids, they might be liquids, they might be gases, kind of all over the place. Because ionic substances give away and steal electrons, they have really, really high melting points. They cling to each other very tightly. It's very difficult to break them apart. Covalent, not the case. Very easy to break these up, so they have low melting points and low boiling points. And this is going to be important in one of the labs that you do. Ionic substances have very extended lattice structures. Their solids have very, very ordered components. Not necessarily true of covalent. Ionic substances, when you put them in water, they dissolve, and then they're strong electrolytes. They will conduct electricity. Covalent, they might dissolve in water, but they're not going to conduct electricity. And remember what I said in regular chemistry. With ionic, you have a metal and a nonmetal combining. So if one's over here on the periodic table and the other one's over here, it's ionic. If they're both over here on the periodic table, 2 nonmetals, it's going to be covalent. Please know there are exceptions. Oxidation charges are not the same as the charges on the periodic table, and sometimes they can get kind of high, especially the transition metals. When the transition metals oxidation numbers start hitting +4 and above, even though you might have a metal with a nonmetal, maybe you've got manganese with chlorine, you would normally think, ionic. Well, when those charges start hitting the +4 and the +5s, they actually act more covalent. So sometimes an ionic compound will have covalent nature. It gets kind of weird and kind of complicated, but we'll talk about that a little bit more when we do the electronegativity differences. I know we talked about Lewis structures, but let's talk about those again. We're going to really start looking at drawing out the Lewis structure, not just for one element, but for an entire molecule. Rules that you need to remember about Lewis symbols or Lewis dot structures is that each side of an element needs to have 2 electrons on it. Most of the time, there are some exceptions. So let's say you have oxygen. Oxygen has 6 valence electrons. You're going to put 1 on each side, right, left, top, bottom, before you can double up. And anytime you do double up, we always try to balance out the dots. So if you put 1 on the right, you're going to put the next one on the left. If you're going to put 1 on the top, the next one goes on the bottom. And then you're going to add 1 to the right, the next one will go on the left. We always want to try to balance that out. Please be careful of looking on the internet. When you look on the internet, a lot of times, I think what they do is they try to show Lewis structure with shape, and we really shouldn't do that. So oxygen has 6 valence electrons. It should be either a single dot, 2 dots, 2 dots, or 2 dots, 2 dots, single, single. And a lot of times on the internet, it'll have 2 dots on the top, 2 dots on the side, and then single on the bottom, single on the side. I don't want you to do that. So be careful about going to the internet and looking stuff up. Use your brain. Atoms are going to gain, lose, or share electrons in order to have the same number of electrons in the nearest noble gas. So sodium, all it needs to do is get rid of 1 electron, and it's going to be like a noble gas. Fluorine wants to gain 1 to act like a noble gas, so keep that in mind. All the noble gases have 8 valence electrons except for helium. He only has 2, but that outer energy level is full. So once helium has 2, it's like a hotel. No vacancy, there's no more room. Atoms gain or lose electrons to hit what's called the octet rule. They want to get to 8. Keep in mind there are some exceptions. There are some elements that love to have 10 electrons around it, like P. There are some that will take 12 around it, like S. So just know that there's some exceptions to this rule. For the record, you don't hear a bomb in my kitchen. It's my cuckoo clock. How do you draw a Lewis structure for a compound? Well, you need to know, first of all, how many valence electrons there should be altogether. So let's say you have something simple like H2O. Hydrogen has 1 valence electron, but there are 2 of them, so now we're up to 2. Oxygen has 6. 2 plus 6 is 8. So your total number of valence electrons is going to be 8. Start by drawing a skeletal structure. So figure out who's going to go in the middle. Usually the least electronegative is going to go in the middle. You will never put hydrogen in the middle. Hydrogen can only form 1 bond. It's like somebody with 1 hand. They can only shake 1 other hand. So never put hydrogen in the middle. Most electrons or elements are going to get 8 electrons. No, there are exceptions. Hydrogen doesn't get 8. Boron doesn't get 8. Anything in the boron column, anything in the beryllium column is not going to get 8. Columns 1, 2, and 13 are only going to get 1, 2, or 3 electrons. That's it. Aluminum can form 3 bonds. Beryllium can form 2. So keep those in mind. So start with your skeletal structure, connect everything, give everybody who deserves it 8 dots. And then count. If you have the right number, you're done. If you have too many, you need to make some double and or triple bonds. So if you have too many, erase 1 dot from 2 different atoms, draw a line to connect them. Recount. If you still have too many, erase another pair of dots and either do another double bond or maybe a triple bond. We will actually draw lots of these. We'll play with them. And we're actually going to try and break all the rules. We're going to throw the octet rule out the window and we're going to go crazy with these. And then we're going to do something called formal charge. We're coming up to that here in a minute. Formal charge will give us an idea which Lewis structure may actually be the most stable. And sometimes it's not what you think. It's actually kind of fun. I gotta be honest with you. I really think this next part is kind of fun. So when you draw all these Lewis structures and we pull out all the stops and we break all the rules just to see how many different ways we can make something, how do we determine which one is probably the most stable? And of course, we don't know because we can't see molecules. We can't see the bonds between them. But we're going to apply something called formal charge. It's not a real thing. It's not a real charge. It's all theoretical, but it will give us some ideas. So you're going to make the Lewis structure. And then we're going to calculate what's called formal charge for every atom in the structure. Now the book is going to tell you that formal charge is the number of valence electrons minus 1/2 of the bonding electrons minus the non-bonding electrons. Well, one day I was doing this and I'm like, this is stupid. So I came up with my own saying it is formal charge is equal to the number of valence electrons minus dots minus lines. It's actually pretty easy. And we'll go over this together. We'll do one of the assignments together, and it's a lot of fun. But the dominant Lewis structure is this one. It's the one where the atoms either have formal charges closest to 0, or where, if they do have a charge, the charge makes sense. And what do I mean by that? The negative charge is probably going to be on the atom that is most electronegative. You wouldn't give nitrogen the negative charge and oxygen a positive charge. That just doesn't make sense. And the sum of all the formal charges still needs to add up to the charge for the whole structure. And again, these aren't real, they're just theoretical, but they do help us to determine which Lewis structure we think may possibly be the most stable, and it's not always what you might think. One of the things you need to do when you're writing Lewis structures is to show resonant structures. They're just alternate but equivalent structures, and here's several examples. So the first one's ozone. We know there's a double bond on ozone, so you either draw it with the double bond between the second and the third, or between the first and the second. You can see the ion for nitrate, NO3. There's different ways to draw it, and if you do go count, and I encourage you this, you do get the right number of valence electrons every time. And then there's one other structure. Now that one's kind of a weird one. If you look at the ring structure, it's benzene is what that is. You'll notice there are double bonds, alternating double bonds. So you can either have the first picture or you can have the second picture. Well, one way to do that without having to draw them both twice is to draw the hexagon with a circle inside. And that circle just shows resonance. It just means there's alternating double bonds. It's pretty easy. Let's get into the exceptions on the octet rule. Molecules and polyatomic ions contain an odd number of electrons sometimes, and so you have to do something kind of funky and weird. Take a look at this NO over here. Do you notice on the N there's just a single dot? Yeah, weird, right? Or you can draw it with a single dot on the O. Another one that we do quite often is the methyl group, which is CH3, and CH3 has a charge on it. So that's another one where you might have C with just a dot. Normally we don't. Normally that is just not something we do. I talked about this earlier, but let's look at the second bullet. Notice that sometimes molecules have less than an octet. B, for example, can only bond 3 times. So B is only going to have 6 electrons on it. That's it. But notice the fluorines each have 8. Let's see, next one. Ooh, when we go above and beyond the octet rule. Exciting. This is an example of P. P likes to have 10 electrons around it. So what I recommend is, for example, PCl5. Well, put the P in the middle, put all the C's around it, give everybody who deserves 8, count it up, and you will get the right number of valence electrons. Sometimes when you're doing this, like XeF4, do the math real fast. Let's see, Xe is 8, F is 7 times 4 is 28, so what, a total of 36? Am I doing my math right? I think so. Well, when you do this one, you're going to put Xe in the middle, F, 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 put all the dots around the Fs, and you're going to count, and you're going to be like, oh, I'm shy 4 electrons. So what you do is you just add pairs to that middle Xe. So Xe is actually going to get a pair of electrons, another pair of electrons. Each of the Fs will have 8, and you'll get your total of electrons. So sometimes it's pretty easy usually to figure out what you need to do with all those dots. We're not going to agonize on this next part, but I wanted to just show you in case you ever take an upper level chemistry class. But the transition metals, they're kind of odd, you know, the D block elements. Because of that d orbital and how many electrons can go in there, the octet rule does not always apply. Just know that the electrons that are lost first are from the subshell with the highest value of N. I know we've already looked at this in another unit. So for example, if a transition element is 4s2, 3d6, the s orbital electrons will be given away first, and then the d electrons may or may not be lost. Just know that the transition metals can be kind of odd. So unfortunately, one thing the Lewis structures do not show us is bond polarity or electronegativity. You guys know that electrons can be shared equally or they can be shared unequally. So if I've got this beautiful chocolate chip cookie, I'm like, I'll share it with you. I can agonize, cut it right down the middle, measure it out, and we can each have an equal half of a cookie. Or I can break off a crumb, give you the crumb, I can take the rest of the cookie, and guess what? I still shared. I just shared unequally. So in order to do that, we're going to have to do a little calculation. And I just love this cartoon. It shows the difference between the two pretty nicely. In a non-polar covalent bond, everything is being shared very, very equally. Look at the two hydrogens. They're pulling on the electrons equally. Hydrogen chloride, on the other hand, Cl is way more electronegative and is pulling those electrons way more tightly and winning the tug of war contest. So how do we determine bond polarity, or even how can we use some math to determine ionic versus covalent? And please note right now, this is not foolproof. I mentioned earlier that even though you think something is ionic, like copper with iodine, well, metal, non-metal, ionic, right? Sometimes they actually have covalent properties. Kind of cool. So electronegativity, let's just redefine that. It's the ability of an atom in a molecule to attract electrons to itself. Typically, this increases as you go across a period. You guys know that fluorine is really electronegative, but sodium is not. It's going to decrease as you go down a group as that atomic radius gets bigger. So what you do is you use one of the many different resources available to us, and we find the electronegativity value for the two elements. You subtract and you compare. And then you need to compare that number to some sort of guideline. And please note, not all resources agree with this breakdown here, but we'll just run with this one. 0 to 0.3 or maybe 0.4 is what we call nonpolar covalent. We look at the electronegativity difference and we decide, you know what, that's not much of a difference. They're sharing pretty equally. Somewhere between 0.3 or 0.4 and 1.7, maybe all the way up to 2, is polar covalent. And then 1.7 plus, some resources say 2 plus, is ionic. So just know that somewhere between 0 and about 0.4 is nonpolar, between there and about 2 is polar, and anything above that is ionic. So when there's a polar covalent molecule, we need a way to show which one is more positive and which one's more negative. Like think about water, H2O. We know O is the negative one and the H's are positive. So we'll use that little symbol. We won't write a +1 or a -1 because they don't really ever have a full positive or negative charge. We just use that little weird, I don't even know what that is. It's some Greek letter, some weird little symbol that shows that this is the positive region and this is the negative region. So we're learning right now about drawing the Lewis structures, about the shapes, because in the next unit, we're really going to get into intermolecular forces. Why does water stick so well to other water molecules? And that is because when you draw the Lewis structure, you see that the oxygen has those extra electrons around it, and that makes it negative, and then the hydrogens are kind of positive, so the positive of one water molecule will be attracted to the negative part of another water molecule. So looking at polarity really does explain a lot of these properties we see. Also note that polar, which is covalent, can be attracted to ions. Water has a positive and a negative region. Water is covalent, but water is attracted to, say, sodium ions or chlorine ions that are dissolved in it. And like I said, we're going to get into that more in the next unit. A dipole moment is going to increase as the charges increase or the distance increases. The larger the dipole moment, the more polar it is. So the farther apart those atoms are, the more the dipole moment increases. As bond length increases, the electronegativity difference decreases, and so your dipole moment is going to decrease. And experimentation shows us that even in ionic bonds, the charge isn't always a set +1 or -1 or +2 or whatever. I mentioned this earlier. Sometimes even in an ionic bond, we have some covalent bonding happening. So even though we say they're giving away and stealing, sometimes there's a little bit of sharing going on. It really is a lot more complicated than we make it out to be.